Hi and welcome back. We're going to be continuing from our previous topic, which was correlation, and move into regression. More specifically, we're going to talk about linear regression and ordinary least squares in the next few videos. Now, a big difference between correlation and regression, while both work on linear relationships between two variables, the biggest difference between correlation and regression is that correlation only measures the strength of a linear relationship between two variables. So it only tells whether the relationship between two variables is highly linear or highly non-linear. The value of correlation is a single statistic which is ranging from -1 to +1 as covered in our previous lectures. And the closer it is towards +1 or -1 is the stronger is the linear relationship. But there's a shortcoming over there in correlation. While it measures the strength of the linear relationship, it does not tell us anything regarding the linear relationship itself. So what we do in linear regression or regression analysis or regression model building is to try and figure out that relationship. What is that function? So the process through which we actually derive the function between the two variables is known as regression analysis. And regression itself is simply the linear function between two variables. Now, as we all know, or some of you may not know, a linear function is simply the equation of a line. And the line follows the formula which is y is equal to mx plus c. So I'll try and draw it out a line over here so that we are a little more comfortable regarding regression. Supposing I have two axis x and y. So this is a horizontal axis x, this is a horizontal vertical axis y over here, and I have a line in this two-dimensional space. This line can be of any particular slope. It could be like this, it could be parallel to y-axis, it could be parallel to x-axis, it could be at an angle. It doesn't matter as long as it's a line, and a line has got no endpoints specifically. So this line can theoretically extend all the way till infinity over here and all the way till minus infinity on the other side. So we're looking at this particular line segment over here, and the equation of this line is y is equal to mx plus c. What this equation effectively means is that at any point of in the line, right, if I know the x value, so this is the x value at this point of line. At this point, the value of x is the intercept of this parallel line over here. So this is the x coordinate of this line. So if I know the value of x, I can always know the value of y, which lies over here. And this follows the function that y is some function of x. And if I open this function follows the formulation of mx plus c. So what is m over here? So m is defined as the slope of this line, or the slope or the angle this line makes with the x-axis. One way of looking at the slope is that if I start to solve this particular line as a triangle, so I'll pick up any segment over here. So let's pick up this particular segment over here, and I'll make a right angle triangle over here. So the slope is the tan of this angle theta, and how this works is that for a unit change in x, so this is the unit change in x over here in this particular triangle. What is the change in y, where y is the perpendicular over here, right? So if I change the value of x by this amount, y changes by the measurement of this amount. So delta of y divided by delta of x is known as the slope of the line, or a unit change in x gives us how many unit changes in y. So that's the slope of the line. And c, which is known as the constant, is simply the point at which this line intercepts the y-axis. So if I go ahead and I extend this line at this point in time over here, the line goes ahead and intercepts the y-axis. The value of x at this point is 0 as the origin. So if I put the value of 0 into this equation, y becomes m into 0 plus c, which is essentially says y is equal to c. So the if I put in the value of 0 into this function, y essentially becomes equal to the constant, and that is known as the y-intercept of the line. So this is how typically the equation of a line works out to. And how can we use these properties of a line or a line segment or the formula y is equal to mx plus c to start building predictive models or regression models? So let's have a look at how this works. So a few terms that we must learn or we must be very familiar with. In a line segment, the formula or the equation of a line always follows the convention that y is equal to mx plus c, where y is also called as the dependent variable and x is also called the independent variable, i.e. y is on the left hand side and x is on the right hand side. Now, while these are the terms, y is called the dependent and x is called the independent variable, it does not mean that y is dependent on x. We are simply fitting in a model. So going back to our previous lectures where we talked about correlation and causation, just because two variables are correlated does not mean one variable is caused by the other or vice versa. It holds true in linear regression as well, that while we can denote the function between y and x in form of a linear equation, the term dependent and independent variables are only terms. It does not actually imply that by changing the value of x, the value of y will change as per the line segment. But that's the convention that we use. M is also known as the slope of the line and C is known as the constant or intercept. It's called intercept because it intercepts the y-axis at a certain point. So the point at which it intercepts. So this distance between origin and the way place it intercepts the y-axis, this distance is known as the y-intercept or the M. So the distance is measured and called out as M, or sorry, not the M, sorry, the constant. I meant to write the constant over here. And one way of interpreting this is, if x is 0, what is the value of y at that point in time? Right? So this was the basics of a line segment and how we go about formulating the formula for a line. So how does this work with regression? So the way regression works is, let's say I have two variables x and y. So I'm going to create a new clean sheet over here. So assuming that we have two variables again, x and y. So let's say I have x variable over here, I have y variable over here, and I have observations x1, y1, x2, y2, x3, y3, all the way till, let's say, xn and yn. Now this could be the age and weight of individuals, it could be height and weight, it could be age and income, it could be any two variables in a data set of paired observations. The only restriction is that they have to be on a continuous scale. They need to be continuous variables and not nominal variables. So regression, like correlation, is a parametric technique. It relies on the fact that the two variables have both magnitude and direction, i.e. they are vector variables which can be plotted onto an n-dimensional space. So I have these two variables and I want to fit in a function that y is some function of x, so that if I know the value of x, I can start predicting the value of y. So by knowing x alone, I should be able to predict the value of y, and this function needs to take the form of a line. So when we build regression models, we call that function or the linear function as beta naught plus beta 1x plus the error term. So over here, beta naught is the intercept and beta 1 is the slope or parameter estimate. We call it the slope or estimate for x as the independent variable, and e is the error term in our regression model. So I'm going to talk about the error term a little over here, but before that, how do we actually go from having a data set of observations to a function where we fit in y is equal to beta naught plus beta 1x plus the error term? So let's try and plot this on a two-dimensional graph, and what do we get over here? So assuming that we have two variables x and y, and the assumption is that there is some correlation between them. So regression will not work if the two variables don't have any correlation.
And we've already covered that correlation means that two variables have some sort of a linear relationship, and the linear relationship is fairly strong. So regression works best when the two variables x and y have a strong linear relationship between them. So assuming that there is a linear relationship between them, let's have a look at how the scatter diagram may look like. So what we do is we're going to plot the data set in terms of a two-dimensional graph with x and y axis for the variables x and y. And what happens is, assuming that we have some sort of a scatter diagram, and let's assume this is the scatter diagram between x and y. Right, so we've plotted those n observations onto a two-dimensional graph. So what we're going to do, or what regression wants to do, it wants to figure out, or it wants to identify a line segment. A line segment could be anywhere. It could be a line like this, it could be a line like this, it could be so we can have infinite number of lines. So we want to figure out, or we want to identify the line which best explains the relationship between x and y. So, or the line of best fit. So to put it down, we need to identify line of best fit. So how do we go about identifying a line which is the best fit for the data set that we have? So let's draw out a hypothetical line over here. So let's say this is hypothetical line 1, and we're going to call this as line 1. What we do is, for line 1, we identify what is the error, or by how accurate this line is capturing the relationship between the two variables. So we know that the function that we want to build is y is equal to function of x. So if I start putting in the values of x, it will start predicting the value of y, but there will always be an error in our prediction. So assuming that function of x does not give us the actual value of y, it gives us function of x gives us an approximate value of y, which we will call y hat. So there will always be an error between what the actual value of y is and what our function is going to predict. So if we run with this error, so we can always calculate what the error at each point in x that we generate is going to be like. So I'm just going to create some space on top to actually draw this out. So I'm going to I'm going to erase uh, a bit of the area over here. So I need to write it down. Let me bring this and make this even bigger so that we can quickly. Yeah. So I have it over here. So we know that the y is equal to some function of x plus the error that we get, or y is equal to function of x, we can replace it by y hat plus error, or error is simply the difference between y minus y hat. Now y hat is going to be the value of y for any given value of x as per the line. So if I look at the x over here, so this is the value of x, and for this value of x, the line actually gives us a value of y hat is over here. So if I want to figure out what the error is for each observation that we have, we can figure out the difference between the line and that particular observation. For example, let's look at this particular observation. For this particular observation, we have the value xi and yi, right? But for this value of x, if I look at the line segment, sorry, let me draw that again. The line segment, if I look at the value of the line segment for this value of xi, the line segment is actually predicting a value over here for y. So this is going to be my y hat. But for this observation, the actual value of y lies over here. So this is the actual value of yi. So the error in this term is this difference over here, or this distance. So this is how I find out the error at each observation. For this particular observation, the difference is, let's call this y hat I. So the error over here is yi minus y hat I. And for I equal to 1 to n, for each of these dots or each of these observations in time, I can actually figure out what is the total error. So if I use the summation option over here for my complete data set, EI, so let me just draw it again correctly. Let's call it summation EI, where I is ranging from 1 to n. That is for each observation in term, and I will add it up, is simply going to be the summation of I is equal to 1 to n of yi minus y hat I. So that is going to be the total error in my observations. So what I can now start doing is, for line 1, a hypothetical line, I can compare the error, or I can draw out, or I can calculate the total error that line 1 has for my data set. Similarly, can I hypothetically create a line 2, line 3? A line 2 could be something like this, a line 3 could be something like this. So I can create infinite number of lines. Then I can start comparing the error across the lines. Now, if I start to do that, there is one problem that I see over here. For example, for this particular observation, the error is positive because yi is greater than y hat. But let's look at this particular observation. For this pair, I'll call this as xj. The value of y is over here. This is yj. But the predicted value of y lies on this line over here, which is over here somewhere. So the error over here is this distance in the error. So if I plot out this error, which is yj minus y hat j, in this case y hat j is greater than yj, therefore the error is going to be a negative value. So in some cases the error is going to be negative, in some cases the error is going to be positive, depending on where the point is. If the point is above the line, I'll get a positive error term. If the error is below the line, I'll get a negative error term. If I add up all the errors directly, the negative and positive errors might cancel out, and I might get an average or a total error of equal to 0. So in this case, if I compare various lines, right, I might have a line where the total error is 0, and line 2 where total error might be slightly positive or negative, or it might be another line which has a total error of 0. So it becomes difficult to just compare and identify the line of minimum error directly like this. So we need to do a transformation which is going to take care of negative values. So one transformation which converts negative values to positive values is that we can square it. So if I look at the error term over here and I square the error term, so the error term is simply yi minus y hat I. And if I square this term and then add it up, summation of I is equal to 1 to n. I look at the squared error term, so this will give me the summation of error term I is equal to 1 to n and ei. So instead of looking just the error, I start looking at the squared error. And since there is a summation involved over here, so this becomes the sum of squared errors, or to be short, I'll just start calling it SSE. So SSE stands for sum of squared error, and the error is simply the difference between the predicted value of y based on the line and the actual value of y. So actual value of y is yi, the predicted value is y hat I. So I square the error term and I add up the error for all the observations in my data set, and that becomes the total sum of squared error for line 1. I can hypothetically do this for line 2, line 3, line 4 and all the possible lines, and I select the line of the minimum squared sum of errors, or if I put it over here, the minimum SSE. So line with the minimum squared error term becomes my regression line, and the formula or the equation of that line becomes the regression equation between the two variables x and y. So let's assuming that line has a formula of beta naught plus beta 1x, where beta naught is nothing but the intercept, the y-intercept, and beta 1 is the slope of x and y. So this becomes my formula. So I can now put this into, so let me just bring up another, so I am running out of space. So let me just put up paintbrush over here. I don't want to delete the previous slide. There's a lot of data over there. So now I've got the regression formula of the line is beta naught plus beta 1x. So I know that y hat is now beta naught plus beta 1x, and y minus y hat is the error term. So therefore y becomes y hat plus the error term in the regression formula, or y simply becomes beta naught plus beta 1x plus the error term. So this is my regression formula over here. Now the error term cannot be predicted, so error term is always a random error, so that's not something that we will be able to predict. But we, for any given value of or any given data set where I have a variable y and a variable x, all I need to do is I need to estimate beta naught and beta 1, and this is estimated using OLS. So why do we call it OLS? Because we are looking at the squared error term, or the sum of squared error, and then I'm finding out what is the line which minimizes the sum of squared error. So that is why we call this as ordinary least square estimation, right? So the term OLS stands for ordinary least squares, and it is called ordinary least squares because we are simply figuring out the line which has the least sum of squared errors, therefore OLS, or ordinary least squares. So this is how an OLS regression is actually performed between two variables. So quick recap. So an infinite number of lines can be plotted through the scatter diagram between two variables. So I've got these two variables just like we explained. So these are the two variables that we have, and we have infinite number of observations over here. And what we can do now is we can calculate the error of each line separately. So I calculate the sum of squared error for each hypothetical line. Errors can be positive or negative. The way we calculate error is simply the distance between the observation and the hypothetical line that we have, and this distance is always measured on in terms of the y-axis. So we don't take the perpendicular distance. So this distance is not to be taken. We only take the vertical distance. So the vertical distance between each observation and the line. So I have n number of observations. Some of the observations above the line, some of them are below the line. So the errors can cancel out each other. To make sure that the errors remain positive, we square the error term, hence the term squared error. Identify the line of minimum sum of squared errors. So for all the hypothetical lines in my scatter diagram or in my two-dimensional space, identify the line of this where the sum of squared errors is minimized, and therefore we get the name OLS, ordinary least squares. So again, note, error is calculated as deviance from the line as parallel to y-axis and not the shortest distance between that observation and the line. And this is how OLS regression works when we generate a formula between the two observations. And again, the in regression analysis, we don't use the term y is equal to mx plus c. We more specifically use y is equal to beta naught plus beta 1x, where beta naught is the y-intercept in a line equation. This is also known as the constant, and beta 1 is the slope estimate against x, and e is the error that we have minimized. So e is the error, and the total sum of squared error is the term that we've minimized over here. So error is the random fluctuation in our data set which cannot be explained by our regression models. That's another way of looking at the error, or it's also called the residual in some cases. Now we're going to move on to how do we actually derive the beta naught and beta 1. So derivation of OLS by minimizing errors. So as you can imagine, if I actually start drawing out every possible line in a two-dimensional space and identifying the line of minimum error, that's going to be very problematic. The reason why it's problematic is because if I have, and I'm going to now uh, create a new plot over here. So if I have a two-dimensional space, let's say x and y with the x and y axis. So this is x-axis, this is y-axis. In a two-dimensional space, there are an infinite number of lines. and I mean infinite. So you will have infinite number of lines, and to calculate the error against these infinite number of lines is going to take, it's going to take forever, and then figuring out which line actually is minimizing the sum of squared errors, yeah, that's very cumbersome. So we use that analogy to explain the concept of the line of least squares. But how do we actually do it? So we don't actually go ahead and simulate n number of lines or infinite number of lines and then identify the line of minimum error. So if I look at the formula specifically, I know that y is equal to beta was naught plus beta 1x plus the error term. Right now we already know the value of y and we already know the value of x. So what all we need to do is we need to estimate the value of beta naught and beta 1 such that the error term e is minimized. And this is where we're going to use a little bit of calculus. Now for those of you who are not very familiar with calculus, you can just follow the lecture, and I'm not going to go into actually deriving a partial differential equation, but we will still look at the basics of it. So let's have a look at the equation that we have to minimize. So now supposing that for n number of observations we have x and y such that we have observations xi, yi and I is equal to 1 to n. So what this line essentially is telling us that we have a data set where the variables are x and y, and each observation is a paired observation. So I have x1, y1, x2, y2 all the way till xn and yn. So x1, 1, 2, 3, 4, 5. So what we are essentially saying is we have xi, yi where I is ranging from 1 to n. And the linear regression formula that we are following is that for each observation of y or yi is simply beta naught plus beta 1 xi plus error term. So for each observation it's beta naught plus beta 1 xi plus the error term ei for each observation. Right, so if I put in x1, x2, x3, x4 over here, I'll start getting the values of y1, y2, y3 and the error terms now. Now beta naught is the y-intercept, beta 1 is the slope of the equation, the error is the error of the in the model. Now the problem that we have to solve is we have to identify beta naught and beta 1 such that the summation of errors or the summation of errors is minimized, i.e. the line of minimum error of sum of squares. So we have to figure out where the error term summation of I is equal to 1 to n ei whole square is minimized. So the sum of squared error needs to be minimized or limit approaching the minimum value if you are a little bit mathematically oriented. So let's bring error term onto the left hand side and the equation on the right hand side. So if this is the equation that we want to minimize, so how do I get error term on the left hand side? So let's start off with this equation itself. Right, I know that yi is equal to beta naught plus beta 1 xi plus ei. So I'll just write it down, beta naught plus beta 1 xi plus the error term I. So bringing error onto the left hand side, so I'll bring error term over here. Ei is nothing but yi minus beta naught, sorry, minus beta naught. And if I bring the error term again over here, minus beta 1 xi, or I can write this as yi minus y hat I. Now I need to minimize the squared error term, so this essentially becomes this ei whole square is equal to yi minus y hat I whole square. So now that we've reached this point, I'm going to now shift over to MS Paint and don't save over here. So we reach this point that ei is equal to yi minus y hat square, and if I look at the presentation, right, so we have got therefore ei is equal to yi minus beta naught x plus minus beta 1 x1 square. So let's keep it into our original for formation itself. So I know that I have to minimize ei whole square summation of I is equal to 1 to n. In fact, let's keep it here where it draws a little better over here. So I'll just make a new sheet. Just bear with me a little. So I know now that what I have to minimize is equal to 1 to n ei whole square, which is equal to yi minus y hat I whole square. So substituting the value of beta 1 and beta 2, so I know that yi is yi, but y hat I is nothing but beta naught minus beta 1 x whole square, and the e value over here remains the same. So now what I can do is I can actually differentiate this the right hand side twice. So once I will differentiate it using beta naught, so it could be del by del beta naught becomes equal to 2 into yi minus beta naught minus beta 1x, and this becomes equal to 0. And the other time I can do is I can differentiate by del beta 1. So once I get these two different equations, I get two equations, and I've got two unknowns that I need to solve in terms of y and x. So I need to solve for beta naught and beta 1 as some functions of y and x, and all I need is two equations, and that's what differencing is actually going to do over here. And once I difference and solve it, I get the value of beta 1 x and beta naught x in terms of only y and x. So beta 1 is essentially the multiplication of x and y whole bar minus x bar into y bar divided by x square bar minus x bar whole square. So essentially a function of only x and y observations, and again beta naught is simply y bar minus beta 1 x bar. So now using only x and y, I can actually find out the intercept or the y-intercept as well as the slope which best fits or minimizes the error between the two terms. And that's where we're going to actually use differencing, and we're not going to go dwell too much on differential calculus over here because that's out of scope for our video lecture series. But what it was essentially doing over here was I was just giving a glimpse or an insight of how actually differential calculus is used to minimize the error term. So we use the method of actually figuring out the minimum possible value of a function and then solving it for the two unknowns beta 1 and beta naught. So these are the two unknowns that we wanted to calculate as a function of both x and y, and how this actually works. So I'm going to give you an example of how it actually works. So let's take the dataset HSB2, and I'm going to take a few observations of read and write and take them into a new tab. So I know read and write from a previous exercises that these two variables are highly correlated, and I want to fit a linear equation such that read is a function of write. So I'm going to say read is my y variable and write is my x variable. So x is the input or the independent variable, y is the dependent variable. And what we need to do is we need to calculate the beta 1 and the beta naught. We need to figure out what is the slope and the intercept such that it follows a function that read is intercept plus beta 1 times write. So let's look at this. So I want to calculate beta 1 first. So beta 1 first is x into y whole bar. So let's take x into y, which is simply the multiplication of these two observations, and there we get x into y whole bar minus x bar into y bar. So now I can calculate the numerator for beta 1. So numerator is essentially the average of, so the numerator is average of x into y. So I just take the average of x into y minus average of x multiplied by average of y. So minus, I take the average of x separately multiplied by average of y. So there we get it. The numerator comes out to be 42. And let's calculate the denominator now. So the denominator is x squared and then the average of that minus the square of the average of x. So let's calculate the square of x first. So let's say x squared is the variable into itself. So this is the x squared. Now I have to look at this is uh, x squared and then the average term of that. So this becomes average term of x square minus average of x whole squared. So I take the average of x. So this is the average of x and I square it. So I multiply it by itself again. And there we have it. We have the denominator as well. So there's something gone wrong with my formula. So let me have a look at this. So there's a negative sign over here. I'll just remove that. Yeah, there it is. So I get the denominator. So beta 1 or the slope is equal to numerator divided by denominator. That comes out to be about 0.579 over here. I need to calculate the intercept as well now. So the intercept is nothing but y bar minus beta 1 x bar. So y bar is average of y minus beta 1, which is the slope, into the x bar, which is the average of x variable. And that comes out to be my intercept. So therefore, read, if I want to calculate y hat, or let's say I'll just call it y hat. So y hat becomes, for each observation, it becomes the intercept plus beta 1 times the value of x, and that becomes my y hat value. I didn't lock this, so let me lock this formula correctly. Plus k2, yeah, there. So once the locking is done, it will work correctly, and that's my y hat. And my error term is simply yi minus y hat. So this is my error in each of the observations, and as you can see, the total sum of error is coming out to be 0.00. So this is how I've actually gone ahead and built a regression model, and I've estimated both the slope of the line as well as uh, the intercept. And if I actually use a regression function, so while I've not covered it, I'll quickly show it to you that if I actually use regression, so there's an option in Excel to automatically build a regression formula, so you don't have to do it manually. So I press regression. Okay, it asks what's the y variable. So y variable is over here, and then it asks what is the input x variable. So I put x over here. I say labels in the first row, press OK, and here we get the summary output. So you can ignore the other output for now because I have not covered it, but here we get is the intercept and the value of the coefficient against right. So I compare this with the actual value that I have. So you can see the intercept is the same intercept which I have got, and the slope against right is the same slope which I have also computed over here. So that's how we actually go about building an ordinary least squares model between two variables x and y, and we estimate it in form of a line where the y or the dependent variable is beta naught plus beta 1 times x variable, or y is equal to mx plus c. And the error term is the term which we cannot actually go about estimating, is the error between the predicted value of y, which is the y hat, and the actual value of y over here in terms of the difference. And that's the error term which is part of my regression model as well. So this is so in this particular lecture we wanted to just cover the basics of a regression model between two variables, and how do we go about estimating it using ordinary least squares, and what does terms like beta naught and beta 1 essentially mean. So quick recap of this lecture before we move on to slightly more advanced terms in regression. So the difference between correlation and regression. So correlation is only measuring the strength of the two variable, the strength of the linear relationship between two variables. It does not tell us anything regarding the linear relationship. In linear regression, what we are trying to do is we are trying to find out what is that linear relationship, and any linear relationship follows the formula or the equation y is equal to mx plus c. So y is always termed the dependent variable, x is termed as the independent variables, but that does not mean y is dependent on x or x is dependent on y, or vice versa. Uh, that's only the terminology used. And m is the slope between y and x. So one way of looking at the slope is how if I change x by 1 unit, y is going to change by m units. So that is a unit change in x gives us how many unit changes in y. That gives us the slope of the equation. C is called the constant or intercept, or it is the point or the intercept where it touches the y-axis. So this is the way, the area where the line is actually touching the y-axis. At this point, you can see the value of x is 0. So the intercept is also interpreted as the value of the left hand side of the equation when x is put to 0. If I put x equal to 0, m multiplies by 0, so essentially y becomes c, and this value is over here is c. So you can see the intercept in this hypothetical line that we see is about 5. So this was the interpretation of a line as a function between two variables. Why do we call it ordinary least squares? Because we try to estimate a line between the two variables which minimizes the total error term or the sum of squared error. So hypothetically speaking, in a two-dimensional graph, we can have infinite number of lines plotted between the two variables. We have to identify the line such as the error in each line. An error is the difference between the value of y as predicted knowing the value of x and the actual value of y. So this line over here, as we can see, this yellow line which has been drawn out over here, so this is the error term for each of the observations. For each dot that you see, we actually calculate this error term in terms of the difference, and we square this term and then we add it all up for all the observations. For each line we get the sum of squared errors. So we then figure out the line which has the least sum of squared errors, and that becomes a regression line between the two variables x and y. And that is the reason why we call it ordinary least squares regression. And how do we actually go about deriving the properties of a line? To identify any line, we only need to figure out what is the slope and the constant. That is all we need to identify a line segment. So to identify the line of best fit, we need to identify only two things in a line, that is the slope and the constant. And by using differential calculus, we can actually calculate both the slope and the constant uh, using only the values of x and y that we have in our data set. And that's what we actually went ahead and did manually, and we confirmed it by using the formula in Excel as well. So this was an introduction to ordinary least squares, where we have one variable, one dependent variable and one independent variable. And in our next lecture, we are going to talk a little bit about the properties of OLS regression as well.